All right, so a couple of things about this picture. So this is a lens here. That's what that piece of the puzzle is trying to model. Is there some sort of converging lens? All right, and some object. So we just, an arrow, all right? It's an object, simple object. It has some height, object height, and there's some object distance. It's so far away from the lens. These are things that are easy to measure. It's 2 inches tall, it's 12 inches from the lens, whatever it is. These are basic things. And if we were to put a surface to project upon, a wall or whatever, then there would be an image formed at some other distance away, and at some other, it'll have some other apparent height. All right. Now inevitably there's some object distance, object height, reality, the actual physical world, where the projection's the same, or apparently the same, depending on how I move the lens or move the object. All right? So those are the basics. As we saw outside by taking a mirror, all right, there's a focal length on both sides of this lens. Okay? And every lens has a focal length. All right? And that's going to be a function of its radius of curvature. So there's always a focal length. We've seen pictures of things that have focal lengths. We actually observed it today when we went out and burnt the stick using a concave mirror. All right, so focal lengths exist. Those of you that have glasses, you can see well through them because they have a focal length. That's correcting whatever's wrong with our eyeball focal length. All right? So those X's represent these spots, and notice little f is the symbol we use for focal length, and it's the same on both sides of this lens. There's one focal length, not two. So we have HO and DO, okay, which makes me think of Hodor in Game of Thrones. All right, Hodor. Anybody watch Game of Thrones? All right, watch Game of Thrones. He's this big, strong dude that could only say one word because something happened to him. Anyways, he died. Sorry, but he died saving children. Yay! So we have those focal lengths, and then DI and HI for image distance, image height. All right. So object for the real thing, image for the fake thing is our notation. And so these principal rays that we talked about in the last lecture, the one that's going parallel to the central axis from the object itself to the lens, one that's going through the center of the lens, and one that's going through the focal point on the object side of the lens, and when it goes through the lens, it goes parallel to the axis. What we notice is that all three of these principal rays converge at the focal point on the other side of the lens. And so would if I just went to the middle of the arrow, I could have three principal rays with the same properties, and that would also focus at the middle of the image of the arrow. It would produce the middle. And so there's infinitely many sets of trios of principal rays that would form an image. That's the idea here. We only need to mess with one set. We don't have to mess with all of them because they all have the same behavior as the others. So let's take a look at what's going on with this ray right here. All right. And by the way, hopefully you remember that this angle here has to be the same as that angle there. Alternate interior angles. So physics is one of those places where your math actually gets used for real stuff, okay? As opposed to math class where not so much, all right? But we absolutely depend on it, as we saw with Snell's law for refraction. It totally, Trig finally paid off in a meaningful way. But here we need to do some analysis about this central ray, and there's some sort of connection that we can do. So we're dealing with right triangles. Hopefully you see that, you know, we have right triangles here, and these right triangles have in them, one of them has the focal length in it, and the other one has the object distance in it. All right, and both have the image or object height going for it. So I have some relatively simple ratios that I can make with those trig things. All right, so let's get to doing the math. So let's look at the tangent of theta, because that's the one that involves the right elements. The opposite and adjacent involve these measurable things. So why would I pick tangent? Well, one, I already know in advance that that's how it works. Okay, surprise, surprise, the teacher knows the evil trick that they're playing on students. But practically speaking, I'm concerned with the connection between object height and object distance, image height and image distance, and the tangent to this angle involves those two things on both sides. On the object side, tangent involves the two easy to measure things. On the image side, it involves the two easy to measure things. Whereas sine and cosine don't do that. It's not easy to measure the length of that central ray from the tip of the object to the middle of the thing. I'd have to do more work than the other stuff, all right? Because the object height is a fixed height. It's not changing, all right? And if I lay a ruler out on the central axis, then I know how far away it is. Otherwise, I have to do more work on that. So tangent of theta will be two things. It'll be HO, be the opposite over here on the left, and the adjacent, which is object distance. This measure up here is also what's down there. But on the other side, the opposite of theta over here on the other side of that thing would be the image height over the adjacent, which is the image distance, how far away the image appears to be after being projected onto something through the lens. So this right here, I have a simple proportion. Remember proportions? Intermediate algebra, college algebra, proportions. I have a proportion here. Ho d equals high do, if we wanted to spell it out. So whatever that does for us, okay, if I know 3 out of 4 things, I know the next one. All right? So what this is aiming at is rules for magnification. All right? So these projectors that we're watching, you know, this live recording, on the screen, you can focus that lens to make things bigger or smaller by changing its distance. You can zoom in or out on things, all right, how this thing works. So I have this going for us. Yay. What about this connection, the alpha angle here? Oh, well, let me write this one. So this is the central ray height and distance connection. All right, so this one here in red. Now let's get to this thing in blue. So alpha is also going to be this one here. that angle is also going to be alpha. Not as easy to see. Let me be careful there. Actually, I think that's beta, not alpha. Let me, alpha is going to be here. There we go. All right. So if I want to work on the tangent of alpha, let's see what we get. So over on the big side where it's easy to see, I'm going to have opposite to alpha will be h naught, or the object height itself. However, this length here is part of DO, but it's DO minus the f, the focal length. So I have the difference between the object distance and the focal length. It's shorter. It's not as long a distance from the object because I'm stopping at the focal length. Okay, but this is the focal length connection. This angle here, alpha, is dealing with a connection here at the focal length. All right? And on the other side of things, it would just be the image height and the focal length on the other side. All right. And then tangent of beta, running out of room here. So we can try to deal with this part of the puzzle. Same sort of situation. Here the object height and focal length are part of the puzzle, but the image height is offset from that focal length by that piece of the puzzle, which is just the image distance minus the focal length. So we have three relationships, and the blue and the green highlights have all the same terms. They're all those three terms, or four terms rather. And then they all share the same set of measures. Some of them are fixed measures, some of them are easy to measure quantities, and then the other ones are ones that we want to compute. All right. So I'm going to add a thing here and kind of summarize the math a little bit. So what do we get? We get that this ratio is equal to that ratio, that there's a connection between the object height relative to the image height is the same relationship as the object distance is to the image distance. But this also ends up being equal to, if we do all the math, which I'm going to spare you, these other ratios that come from the trigonometry, right? So by just doing right triangle trigonometry on this situation, we come up with this series of proportions from which we can try to craft some useful tools. So we're working on the thin lens equation, okay, which is the way that optometrists and whatnot make your glasses, contact lenses, laser surgery. They have to do some of this to figure out how do I modify / create a lens that does the correction that's needed. All right, that's what's going on here. So here's what's common, set of common equivalences that we derive from that math. Okay? Some books show all of this, most don't. They just kind of give you the thin lens equation. They don't show everywhere that it comes from. We have a magnification ratio that is the inverse of this one here. Okay? So let's think about it. Image height per object height. So the image height is the thing that's not real. The object height is the thing that's real. So if this ratio is 1, then your image height is the same as your object height. If this ratio is less than 1, then you're shrinking it, because your image height is smaller than your object height. And if it's bigger than 1, then you're magnifying it. So this is a magnification ratio. And image height will change for 2 reasons. It'll change because you move the lens in or out, or you move the object in or out. That's how you change the image height, because the object height doesn't change unless you take a knife and cut part of it off. All right? Object height is assumed to stay the same. That's the one fixed thing, is the actual object that's in view of this lens. All right? We also can use image distance relative to the object distance. Which one's better to use? Well, the one that I know. If I know how far away the object is, then the image distance will be run this way. And then this is really just a flip of what's above, but it's the way that the rule set is for this game called thin lens. Okay, so we did the math and got what's in black, but the way that it's used is this way. And all it is a flipping it over. So this magnification thing is just 1 over the ratios that came from the other thing. And we did that just because that was convenient to think of it that way. All right? But it allowed us to create an index that makes sense the way that we want to think about it most naturally. Magnification means getting bigger. All right? But it would be 6 to 1 half does the other. Just it would be like that plus minus for electricity, somebody decided, well, let's turn it around so that it makes sense instead of leaving it that way. Flip everything over, then the relationship is constant. So, here, this is just a height ratio. There's just a distance ratio. That's all that's going on there. And then these are just deviations from focal length. And these versions, realize these are all equivalent, but these deviations from focal length things, those are going to be the most useful tools for the lens maker, is because there's going to be an object distance. So how far away are your glass lenses going to be from your eyeball? Okay? So that has to be accounted for so that some small number of changes where I put it on my nose will determine how far away my glasses are from my eyeball. So there's got to be a range of focal length that make the glasses still work. And that's what you should notice is, I can move these around and, in certain spots, everything works good in other spots. You know, if I get them too close, I put them, you know, high as it goes, then things don't work. But pretty much anything, you know, down to the end of my nose is going to work. That's good. We need glasses to cooperate. Okay? What you're looking at here equation-wise is a piece of the puzzle. Now, I think it's probably fully automated these days in the computer system. But last time I was getting these glasses, you know, she was asking me, so what do you do? I'm a physics professor. Oh, you know, so we started talking about the Lindman's equation. She remembered all that stuff because it actually matters in that game. All right. I want to take you on a little journey about averages, because we talked about averages a bit at the beginning of last semester, and averages are really super important. So I'm going to take part of this puzzle and work it out. So here's one of these proportions. And so if I go through the motions here, all right, so let's see, I'm going to get focal length together on one side. And so that means if I pull focal length out, I get d dou per dou plus d, or di, whatever you want to call that. Now, this is an interesting ratio. For one, it has the same basic form that we saw when we had, say, two resistors in parallel, a product over a sum. If you remember from that, or series capacitors. All right. So it has that form going for it. How might we possibly understand that? And then just interestingly here, this also equals the other ratio, the di minus f, per f, which means, and this all works out the same, which is nice, is if I get the all of these things together, then I still have the same ratio. This thing here, these are the same, but they came from different versions of the proportion. All right? So we have this constancy, at least in focal length, can be defined in these other terms. Now, the focal length of a lens is going to be a fixed thing because you're going to create a lens with a curvature. What curvature does it need? Well, the person doing the optics, optometrist, ophthalmologist, whatever, figures out what does the image distance need to be. Okay? And works backwards to a focal length. Creates the focal length, puts it in place, and now you see properly. All right? With these sorts of things. But anyways, I digress. So, and then if I do the third version where I put these two ratios together, the ones that have the deviations in them that are also equal. So all I'm doing here is all the permutations of things that were equal in the proportion. If you go back to the first thing. So what do I get when I try to solve these proportions? And so f squared you're not getting tested on this, so I'm just really just playing that up here. And so the f's, these focal lengths dropped out on both sides, and if you so we've already seen that twice. All right, so it doesn't matter which pair of ratios I put in equivalence, I keep getting back this focal length can be written as a product of the distances, image and object, over the sum, product to sum ratio, which is shown up now a couple of times in various forms here. And so this form, okay, and I'm not saying formula, but this form is essentially a harmonic mean, which you've probably not heard of. You are used to one kind of average value or mean value. That's the statistics word for an average. You're used to an arithmetic mean. Add up all the stuff, divide by the number of stuff. A harmonic mean is essentially the flip of that in a number of ways. One of them is the numerator is the count of the things, but the denominator is the sum of the inverses of the things. All right, so I'm going to try to pitch that in a way that is a little bit more sensible. So let's say that we have a trip that goes from A to B, city A to city B, if you will. And in one context, so scenario one, all right, is going to be 20 miles per hour for first hour, and then 30 miles per hour for the for next hour. And so what's the average speed of this motion? Okay, that's one way to look at it. Scenario two, all right, is 20 miles per hour for first half of the trip. 30 miles per hour for the second half of the trip. What's the average speed? So here's why this is an easier thing to imagine, okay, than the thin lens equation. All right, so I'm going to go back analogously, you know, how does this work? So it's easy. If you go 20 miles an hour for an hour and 30 miles an hour for another hour, assume that the speed change is instantaneous, just for ease of, all right? You magically jump to the next speed, all right? Well, that's not going to be difficult at all, because you know exactly how far you'll go in the first hour and how long it took, and exactly how far you go in the second hour, how long it took, and you get an average speed, okay? In the second one, And so, well, let's do some generalities here. So what I have unequal distance but equal time. And over here, I have equal distance in unequal time. But here's the thing. The speeds are identical speeds. All right? I'm not changing the speed of motion. What I'm changing is what are those speeds relative to? In one sense, those speeds are relative to equal times. That's why, since speed is a distance per unit time thing, I have that regular time average because I'm counting distances relative to equal times. And so those times are acting like a counter of distances traveled at that speed. But in scenario 2, I don't have that. The times are not equal. It's not a time average. I can't do the same math. I can't just add up and divide by the count of the things I added up. It has to be different because of the nature of what's in relation is different. I no longer have equal times to quote unquote count with. All right? So over here, that average speed is easy. It's just going to be distance over time, big D over big T, if you will. And if you go 20 miles an hour for an hour, that's 20 miles, right? And if you go 30 miles an hour for the next hour, that's 30 miles. So you're going to go 50 miles, and you're going to do it in 2 hours. That means your average speed is going to be 25 miles per hour. Okay? Well, over here, the total distance, or big D, if you will, is going to be distance 1 plus distance 2, because they're equal distances. First half of trip, we assume is referring to length. It has to refer to the length because I know the times aren't going to be the same. Okay? And so that's just 2D. So first half, all right, that's just going to be, the time ratio will be that D over 20 miles per hour. And the second half, time 2, is going to be D again over 30 miles per hour. So they have the distance in common, but not the rate, and therefore not the time. And hopefully you recognize that your time, total time, has to be T1 plus T2. All right? And hopefully, if you remember when I did Snell's law, we had to go to total time because the distances, the rates were different, and the distances were. All right? So now I get my average velocity is still going to be big D over big T, but big D is equal to 2D, and big T is the sum of these ratios. So let's be careful here. So average velocity isn't changing. Okay, this is important. This can take us all the way back to first semester. Average velocity is still distance over time. Okay? But the nature of scenario 2 versus scenario 1 is the distance, and the way that distance is measured and time is measured is different in this case. All right? And so what happens here is that we get the D's will drop out, okay? And you'll get 2 over 1/20th plus 1/30th. And basically, what happens here is this ends up being 24 miles per hour. Not the same average speed. Close, but not the same average speed. Right? And so a common mistake would be to treat the second scenario like the first scenario, and you would just be lucky in this case because of the speeds that you were in the ballpark. Maybe the tolerance in the quiz would not ding you, because you were off by only 5% instead of 10 or something like that. All right? So these two cases are different. Now, what this boils down to is a harmonic mean is what we just did in that second scenario. Or it's almost the same as a harmonic mean. A harmonic mean, or average, is defined this way. It is the number of things divided by the sum of the inverses of those things. Okay? That's what a harmonic mean is. And you use this when the situation is like the last one we just looked at in scenario 2, where you have unequal times but equal distances. All right? And so this harmonic mean, if we wanted to just kind of do HM here, for just two numbers, the harmonic mean would be 2 over 1 over A1 plus 1 over A2. Okay, so for if n equals 2, all right, what would the harmonic mean be? And so we can write it this way. And notice all that's different here from like that resistor equation is that the 2 multiple. All right? In that case. And this right-hand side will be that product of some business that we saw when we were back in circuits. All right? So basically our harmonic mean will end up being 2 times the product over the sum. And if you remember, our focal length equation had essentially the same form to it. Only thing that it doesn't have is the double. Or if I had 3 things, it would be a triple. Okay? But keeping it simple, just 2 things. And so what we have here is the structure of averaging a little bit different because the nature of the interaction is very different, what we're accounting for. But yet everything else stayed the same, kept the same speeds. City A and City B didn't get any further apart than they were, but the way that the travel happened was different. All right? And so most of the time an arithmetic mean is a good show, but not always. We can wrap this up here. I'm going to put a box. The classical thin lens equation is like this. 1 over the focal length, 1 over image distance, plus 1 over object distance. Now I end this way and realize that these two are equivalent, okay? Because that classical version of the thin lens equation is precisely what we are used to if you think back to circuits and parallel resistors or series capacitors. If I wanted to know the total resistance or capacitance in those two situations, I would do that product to sum ratio, like you see in blue, which comes directly from solving what you see in red for the thing on the left hand, the variable on the left hand side, right? And the reason for that is you have things working at different rates. And what is the connection to the lens? Well, when light is going through air, it has a speed. When it goes through the lens, work is done on that beam of light, and it changes its speed as it goes through that distance. And so this form, the harmonic mean, is essentially a form that represents how work is done at different rates. There really is no place when you're in algebra class and learning how to deal with those kinds of equations to explain how that's work done at different rates. Unless you do the example that I've given a couple of times now where Chico and the man are painting the garage. The old man paints in 8 hours and the young man paints in 4. It's easy to see the work at different rates, and you get 1 over this plus 1 over that equals 1 over how long it takes them. And that was a harmonic mean. Now, you think back to algebra class, how in the world were we going to make sense of a harmonic mean in algebra class? Right? The best we could do is get you good at pushing symbols around so that when you got to a science class, you could go, aha, it is just math, but it's math that corresponds to reality, and here's why it corresponds to that reality. Okay? So what's the payoff for this group? Well, probably none of you are going to be optometrists. That's every now and then I get a doctor, usually they want to be a surgeon in this course. But the optometrist does this math and understands this interaction because they're an expert in optics. And all this stuff has to be done. And the measurements come from those toys. You know, you stick your face in the viewfinder, you know, and they ask you questions while they're uncomfortably close to you. All right? And they work it all out, and poof, you get a lens. Computer takes these data, makes a lens, shapes it, grinds it, blah, 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 sticks it into frames, and poof, you're off to the races. All right, so that's how that worked. I was more concerned with the reasoning. Okay? And I would say the vast majority of this course, the college physics course, is more about exposure to the facts, but more importantly, why they're facts, the reasoning. So though you will probably never do the thin lens equation, you need to be able to think along this kind of line and recognize that even though, you know, there might be 2 ways to look at a situation with a bunch of givens, which one's the right way to look at it? Okay, I have this situation. Is the average going to be the way I normally think of average, or is the average going to be something different? So you were familiar with arithmetic mean before you came to college. I just introduced you to a harmonic mean. There's another one called a geometric mean. All right, and so they all have their place. Most of the time, the good old arithmetic mean that we're all used to is the right one, but every now and then, it's the wrong one. All right? For example, climate. The arithmetic mean is the wrong mean. Okay? Because, guess what? Sun, going through the atmosphere, it's a big planet. Work is being done at different rates in different regions. And so just taking all of the temperatures from all of the stations and averaging them, That's not a realistic, averaging by the normal means of an average. Not the right average. It'll be skewed. Another reason it's skewed is because you have more monitoring stations near the equator than you do far from the equator. So the way they compensate for that is they just weight it. They have a weighting scheme so that all the ones piling in at the equator are equal in weight to the ones that are far away. So that smooths that out. Smooths? I should edit that, but I'm not going to. That's too much work. It smooths those things out, but if you smooth something out and it's still the wrong tool, you're still wrong. You might get lucky and be close enough, and you would never know. But if you're not, and something breaks or someone's hurt, yeah, that'll be bad. And so one of the goals of this course, and I've said it before, isn't so much that you're going to be a physics problem-solving machine when you walk out. It's that you are going to be a better problem solver within the realm of science in general. Okay, so this course, I think for life sciences, the obviously most applicable directly are going to be the chemistry and biology. All right, physics is so general because it's just the description of motion. Everything is moving. So it's at the edge of the skill sets that are required in that regard.